Dr. Chris. And I'll just read his bio. A lot of people should know him, right? But we'll go ahead. But the president, you just say the president of the United States. We can do something similar, but I'll read the bio for completeness. All right. Dr. Fernando Perez is a staff scientist at Lawrence Berkeley National Labs and a founding investigator of the Berkeley Institute for Data Science, created in 2013. He received a PhD in particle physics, followed by a postdoctoral research in applied math, developing numerical algorithms. Today, his research focuses on creating tools for modern computational research and data science across domain disciplines, with an emphasis on high-level languages, computer computing, and reproducible research. So in 2001, he created IPython while a grad student and continues to lead its evolution into what is now Project Jupyter. It's a collaborative effort with a talented team that does all the hard work. So, he regularly lectures about scientific computing and data science, and is a member of the Python Software Foundation, as well as a founding member of New Focus Foundation. He is the recipient of the 2012 Award for the Advancement of Free Software from the Free Software Foundation. So please give a great applause.
Thanks, folks, for waking up bright and early. I know it's Saturday morning and you're probably tired from yesterday, so I really appreciate you being here, the organizers for inviting me. How's my voice in the back? Is that clear enough to hear me? All right, so please interrupt me if you have any questions, stop me. This is meant to be, we have time, and this is meant to be very conversational. First of all, by state and laboratory regulations, I have to disclose any conflict of interest that I have. These are companies that in one form or another have supported my work, either directly financially or by collaborations with our projects, and so it's important to be aware of that. So this is where I come from. So I was born and raised in Colombia. It's a country at the northwestern tip of South America, right next to Panama, and that's where I come from. Very specifically, I come from Medellin, which is a city nestled in the mountains. For those of you who may have lived in Colorado or have been to Denver, it's right out about the elevation of Denver. Medellin, Colombia is a very mountainous country. It's interesting, the Andes come, and you can even see it on this map, the Andes come all the way down from Argentina and Chile at the south of South America, and right around here in Colombia, they split into 3 branches. So Colombia has this really complicated geography where there's 3 branches of the Andes that create 3 very tall mountain ranges with deep valleys in the middle, and then the right half of the country is completely flat, because this drains into the Amazon basin. So it's basically high mountains and deep valleys on one side, and flat jungle on the other side. Beautiful country, lots of biodiversity. Specifically, the city of Medellin looks like this. It's a very densely populated city, nestled in a valley with beautiful mountains all around it. It's a city that has really, in the last few years, had a fantastic resurgence culturally, civically, in terms of public engagement, in terms of the arts, in terms of very innovative transportation solutions for such complicated geography with steep hills, kind of like what we have here in the Bay Area, and where many of the neighborhoods in those areas are very poor and have been rife with conflict, and the city has been creating really interesting solutions with connecting mass transit systems down in the valley where it's flat, and you can build that with cable systems that provide access to these neighborhoods. So it's a city that is very interesting today, but in the 80s and the 90s, when I was growing up and when I was in college, it was a city that was famous for other reasons. Some of you may recognize who this is. I see nods in the audience. Pablo Escobar, the infamous drug lord, was born and raised there. That was a period where Colombia was a country effectively in the middle of an open war with drug cartels and the guerrillas. This is the building of the central, sort of the Colombian equivalent of the FBI. And so these are the kinds of things that were happening in Colombia at the time. Car bombs that were wiping out. Imagine a car bomb in downtown DC taking out the main FBI building. Planes getting blown out of the sky with bombs. Eventually, Pablo Escobar was killed. This is about 10 minutes from where I lived. So the house where Pablo Escobar was eventually gunned down after an incredibly bloody battle with security forces that took years and with many, many people dead, was about 10 minutes from my house. I was in college at the time. So it was not the most conducive environment for the kinds of things that I wanted to do. It's hard to think about physics. It's hard to think about computing. It's hard to think about mathematics in that kind of environment. This is what I was doing in college. I started actually as an engineer. I started my career. I started studying as an electrical engineer, but I really fell in love with physics, and I switched majors to physics. I was writing code. I very quickly got sucked into computing and to writing code. I was writing, like many people were writing code in the 90s. Fractals were the thing to do at the time, so I wrote my code for fractals. And I learned a couple of things from that period, because at the time I didn't have a computer at home. This was 1990, 1991. I didn't have a PC at home. My mom had a PC in the office, but I could only use it when she wasn't using it. And so it meant coding on paper, which meant thinking a lot about the algorithms, thinking a lot about the code that I was writing, and only getting sort of interactivity and direct feedback once I had access to the machine. And that lesson has permeated my thinking about computing quite a bit. I have the dubious credit of being one of the few people in the world, probably, who has been able to disconnect an entire country from the internet. Even dictators have a hard time doing that. But when I was finishing my undergraduate studies, I was asked by one of my professors to help connecting Colombia to the internet for real. Colombia, this was 1993, 1994. Colombia had a few universities had basically pairwise arrangements with a couple of US universities. But remember, this is before when the internet at the time was still basically growing an academic endeavor. The 1995 change that basically opened up the internet to general use hadn't come yet. So it was very limited, and obviously Colombia was behind. And the Colombian equivalent of the National Science Foundation wanted to set up a proper infrastructure. They were going to drop a dedicated satellite link in Bogota and then connect multiple universities to that, but at least begin establishing normal internet connections in the country. And one of my professors said, hey, you should come and help me. You should come to Bogota. I've been tasked with leading this project. I need you to help me. I said, the internet, what is that? He said, here, read a book. Because this is what I did. I wrote code in Turbo Pascal on floppies on weekends, right? I didn't know what networks were. He gave me a book. I went and tried to help him out to build something that I had no idea could be built or how we would do it. And over the course of a few months, we were basically setting up networks. This was in a facility that was sort of the Colombian equivalent of the Library of Congress, if you will, the National Library Storage and Research Collections Facility. And among other things, what we were doing was also setting up bibliographic databases. Remember, 1993, 94, so these were towers of CDs. These were these towers that could read 50 CDs at a time, so that you basically load all the CD-ROMs of all the catalogs and search any of them. And we had a vendor who was installing these things, and the vendor came over and asked one day, he said, hey, I need a piece of coax cable. Do you happen to have some coax cable to connect one of the servers? And I said, coax, yeah, hold on, give me a minute. No, here's 10 to 6 feet. Piece of coax, go ahead and use it. Off he goes. A couple hours later, phone rings, and I answer the phone. My boss was not in the office. And somebody says, hey, I'm on the satellite engineers here, and the country's offline. And we've kind of bracketed the problem to you guys, because the satellite downlink is fine, and all the cities are connecting fine. Something went down. Can you think of what might have happened in the last few hours? I was like, give me a minute. Go back, fetch the cable from the guy, plug the cable back in. And the printing paper that says never, ever, ever unplug this cable. It turns out the way things were set up, it was literally to a radio station outside of the city with a line of sight modem to an antenna in our roof, and a cable that came down to a computer, the VAX mini computer that was connected to a batch of ISDN modems, a cable that I loaned to the engineer. That's how you take the country offline. So this is me making stupid mistakes and getting myself into things in computing that I really had no training for and no business to. I was trained as a physicist, but you end up trying to make things work. In that context, though, that context of violence and strife actually really kind of grated on me. I had a pretty hard time dealing with that. There are people who can adapt better to those contexts. Those are challenges. I kind of frame it in that context because I'm Hispanic, but I didn't grow up Hispanic in the US. So my Hispanic background is different from that of those of you who may have grown in the States. I don't have the same experiences, but that's the one that I have, right? Which is having grown in a country. I had a happy family. I had the luxury of having the support of my parents for studying and going to universities, but in a country that was effectively in the middle of extremely bloody war all around. And so one of my professors had at some point said, hey, I've heard you like the mountains and the CU Boulder physics department is pretty good. You might want to apply there for grad school. I was accepted, and so I moved. There. This picture is actually taken. This is the physics department in Boulder. That's the tower where my office was. It's a beautiful city in the mountains. I like to climb, and so that's about 30 minutes from Boulder. You can get snow even in the middle of the summer, which is very nice. And when I came to CU Boulder, I started working in a group in particle physics. And one of my professors had this on his door. This is a very famous quote from Hanning from 1962, from a classic textbook in numerical analysis and algorithms. And that quote, actually, I find it it's kind of one of the central drivers of how we build IPython and Project Jupyter. Because if this was true in 1962, it's even more true today. It's even more important. We're drowning in data. Where the computing power, any one of us here in their pocket has probably far more computer power than Hanning ever had a chance to imagine having access to. And so it is even more important that we build tools that help us actually understand, actually extract insight. And today, have access to that also help us understand the context and the implications of what we're doing as well. It's not just obtaining answers, it's understanding what those answers might imply. While I was in grad school, I started developing a little side project called IPython. Who here in the audience uses in their work Python? Quite a few. Who uses R? Quite a few of you. MATLAB, anyone? Actually, quite a few. Okay. IDL, anyone? Okay, this is a harder one. IDL.
I know somebody who uses it.
You know somebody who uses it. So IDL is in decline, and it's also narrower. IDL is kind of the cousin of MATLAB that didn't make it in the marketplace as much. So IDL was created it's kind of intellectually a parallel of MATLAB, but it was created in the world of physics and astronomy. And it's very popular in astronomy, especially in astronomy, and also in earth sciences, but it didn't have the big market success that MATLAB had. The first order, they were very similar. And IDL is what I was using when I started IPython, because I wanted to switch to an open environment, and I really fell in love with the Python programming language. But I wanted to retain that ability of running a bit of code, plotting my data, continuing to run, test things interactively. That workflow that is very familiar in any of the languages that we mentioned already. And so, why did I create IPython? And I can give a lot of intellectual reasons, but it's also important to understand what other motivations there may have been there. And part of it was honestly a crisis. I was in crisis with my PhD. I was having a really hard time finishing my PhD. I was struggling with my dissertation. I was struggling with the topic, with what I wanted to do. My office mate told me, hey, you should check out this Python language. We use a lot of Perl. I use a massive amount of Perl to sort of steer my simulations and my data analysis Python. But I had a really complicated stack with Perl running bash and awk and set scripts and piping into GNU plot and IDL and mathematics. So it was giant jumble of languages. I remember one day I looked on my desk, I literally counted 6 or 7 programming languages, which meant I was just switching syntaxes and switching languages all the time. And the burden of that was pretty high. And colleagues said, hey, you should check out this Python language. And it's kind of like Perlish, but it also can do numerics, and it's a lot nicer and cleaner. I read a little bit about it, and I really fell in love with the language. But I realized, oh, it does have an interactive environment, but it's not as nice as it could be. I'm used to interactive environments like IDL and Mathematica, where I can do lots more other things, and the Python one is pretty basic out of the box. And so I figured, I'm bored. I don't want to work on my dissertation. This thing is cool. Let's go. And so off I went, just an afternoon hack. That afternoon turned into disappearing from the radar of my advisor for 6 weeks completely, getting probably 4 or 5 hours of sleep on average for a few weeks, and going into a kind of a massive coding binge. But it was really motivated because I had a crisis, because I was stuck, because I needed a way out. And I think it's important when we think about our path in these disciplines in our careers to realize that even when things do work out, not always because of the happiest of conditions, and that's okay. And that's okay. It's kind of okay to struggle, and it's okay also, especially, it turns out okay, if you have the right people to help. Because I could not have pulled that off without support. My advisor was extremely patient and supportive. She was an amazing, she is, I'm still in touch with her. She's an amazing, I'm not doing particle physics anymore, but I stay in touch with her. She's an amazing Hungarian physicist who was very supportive and very understanding of what I was struggling with. My wife was infinitely patient in sort of supporting me while I was struggling and giving me all the leeway that I needed. And importantly, as I basically started building this stuff, and actually the act of building something that made me feel again like I could be productive and intellectually active and I could do something, helped me get back in gear with the topic of my dissertation. Even if I wasn't going to stay in life as a particle physicist forever, being able to say, okay, I can make something work. This little side project is actually something where I feel productive and valuable, actually helped me re-engage with my other work. And then I had an applied mathematician at CU Boulder who offered me a postdoc position, and he believed in me. Even though he knew I was struggling with my PhD, but he was willing to take a chance after we talked for a while about physics and math. And that basically said to me, there's a path forward, right? There's a way out of here. You may not want to be a particle physicist all your life, but getting through this project and doing a good job on this will offer a path forward into a really interesting group whose work I was very excited about. And for me, it is also important to keep in mind that, yes,
was the postdoc in physics or in?
In applied mathematics. In applied mathematics, writing, developing numerical algorithms for partial differential equations.
So you saw the path forward, but it was moving you towards something you wanted to do more, is that correct?
Yes, that path forward actually was forward and out in a sense, because it was pretty clear to me that the specific subdomain of particle physics that I was doing my dissertation in, which is called lattice quantum thermodynamics, lattice QCD, which is the study of the internal components of the proton and the neutron and other nucleons, the study of the strong force. It's a very, very narrow sub-discipline of particle physics. And I realized that I wasn't going to try to build a career in that field. His group was developing kind of broad applicability numerical algorithms, and I really liked their work. I knew some people in the group, and I admired a lot what they did. And so it was still related to scientific computing and numerical computing and physics, but with a broader context and in a direction that I was much more interested in.
Thanks.
Please interrupt me anytime, flag me. I'm more than happy to stop. And finally, I do want to mention that I also had an ethical motivation because remember, I said I come from Colombia. In Colombia, I mean, at CU Boulder, I did have licenses for IDEA. I had licenses for Mathematica. I could buy proprietary software if I needed, but the Mathematica license was way cheaper than at the time, $20,000 digital Unix workstation that I had sitting on my desk, right? But that wasn't true in Colombia. My colleagues and my friends and my professors in Colombia, we didn't have access to that kind of software. The cost of a Mathematica, of a full-price Mathematica or MATLAB license in Colombia was prohibitive. And spending resources on that would be literally months of people's salary that you would be spending. So for me, the notion of building my research with tools that would allow me to share with my friends, with my colleagues, with my collaborators back in Colombia on an equal footing, and building science on a completely open platform was actually very, very important. So I'm sort of trying to give a picture of the things that motivated, being sort of honest about my own personal ones, but not losing sight that this is also very important. And what happened was, I did do my postdoc. I did work a lot in applied math, but along the way, because I had started getting involved with creating IPython, with building numerical tools for Python, scientific tools for Python, what happened was I found a community. And I found other people who were doing similar things to mine, building also other tools that complemented what I was doing. And it turns out that there was a community of similar people trying to say, I want to change how I work. So this was an example by John Hunter, who at the time was a postdoc in the Department of Pediatric Neurology at U Chicago, who was working on the problem of understanding how epileptic seizures happen in children, in particular when the children have seizures that don't respond to medication. The only thing you can do is operate. It's a very invasive procedure, but it's a last resort. And this was a screenshot of the highly proprietary software that they were using. And he didn't want to build his research on that, even though he's American, or he was American, he was at a very prestigious medical hospital in the US. He still thought, I want to do my work with something where I can share it. And if later I'm an institution that doesn't have as many resources, that software was one of those things that required a dongle that you had to plug into a USB port. It was one license for the whole lab because it was $10,000 or $20,000 just that license. And the grad students and postdocs had to rotate who could use it. And so he said, I want to do this research, but I want to do it with open tools where I can share it with anyone. So he set out to build a visualization library. Same thing. He said, I'm going to switch to Python. And in his case, what he said was, well, everything else seems to work. What's missing is good visualization for the data, good plotting for the data. So he set out to build Matplotlib, which is, who here has used Matplotlib? Quite a few. So that's how Matplotlib was born. It was to plot. This is one of the earliest screenshots of Matplotlib, plotting EEG traces and the spectrogram of the EEG traces alongside with a BTK view of the 3D location of the electrodes. And a few years later, John, who was actually at my place when he received, he showed me this email. So this is a neuroscientist, right, who's building visualization tools for himself. And he gets an email from JPL, the Jet Propulsion Laboratory at Caltech, that says, hey, this feature that we're asking you about is needed for the Phoenix project, which will be arriving in March. This is in October. It takes longer than that to get to Mars. The thing is in flight, right? So there's a spacecraft in flight, and there's a bug in Matplotlib. The bug was computing accurately the intersection of two ellipses of extremely different diameters. Which ellipses? What's that?
The orbit.
The orbits, exactly. The orbit of the trajectory of the spaceship around Mars and the orbit of Mars around the sun are two ellipses of incredibly different sizes. And if you use an approximation of finite number of segments for the two, you'll never get it wrong, ever, ever, ever. But computing that intersection is kind of important if you're going to try to land a ship on the planet rather than just like zooming by. So this was kind of a pretty high stress for completely personal fun project. Something that started as a personal fun project. Now all of a sudden this was a pretty high stress problem to have to solve. But it's kind of interesting to see that just regular people saying, I want to build my tool, can end up in this situation. By that time, he had a good team. They got to work. They rewrote the algorithms basically the problem.
Hopefully, JPL gave them some money to do that.
Yeah, JPL, not in this case, but yeah, JPL actually has supported Matplotlib development. That's a very good point. And this is a plot of the power sent by the spacecraft as it entered the Martian atmosphere. So it did land, the Phoenix lander did land in Mars, and it was successful. They basically wrote a better algorithm to compute that intersection. I'm sure the spacecraft wouldn't have crashed if it wasn't for that, but still, they were pretty stressed out about it. And I also want to flag that this became a matter, as I said, of community, of building community with people. John became friends in life. We built things together. We met at the first Scientific Python conference. That was a very small workshop with a bunch of ragtag people trying to basically say, I want to build my own stuff differently and openly and collaboratively, rather than either be locked into the traditional academic incentive structure or be buying extremely expensive and locked-in proprietary software. And along the way, we became friends. Our families became friends. Very sadly, he passed away in 2012, which was obviously very difficult for all of us. But I do want to flag the fact that in these processes, we actually have built something which goes beyond simply doing academic and technical work. And it's not just IPython, it's not just matplotlib. Along the way, the Python ecosystem has grown very, very rich. Today, if those of you who raised your hands when I asked if you use Python, you've probably used one or more of all of these tools in your work regularly. But we actually had to justify our existence a lot for a long time. Today, not as much. But back then, this is 2008. And this is a screenshot of a talk that I gave at a SCIAM meeting. SCIAM is the Society for Industrial Applied Mathematics, big applied math conference. This was an annual meeting in 2008. And this is the outline of a talk where I'm basically saying, hey, what the hell is Python to all these people, right? And there's a bunch of like, what is it? Oh, it's a language. You can download it. You can use it. Why would you use it? How do you develop it? Actually, does anyone use it? Sort of justifying, yes, people, you can do this. You can stop using MATLAB. SCIAM is kind of a private hunting grounds of the math works. And so this is kind of going into their home turf and saying, hey, here, we can do things differently. But if the world doesn't give you space, make one. Because it isn't going to give it to you willingly. It has taken us, I don't have to do all of this these days, right? These days, it's a lot easier to ask the audience who has used these tools, and many hands go up. That is very satisfactory. That was not the case. And 2008 is already 7 years after we started this stuff, and some of these projects go back even earlier. The very first numerical layer in Python was started by a grad student at MIT in 1994. And in 2008, we still had to go to these conferences and basically justify why we were doing this to senior people who would say, you are wasting your career. You are throwing away your talent. You should not be doing this. Stop. Your job is to write more papers, not to do any of this stuff. Stop. This is career suicide. This is stupid. You shouldn't be doing this.
Who told you that? Sorry.
I won't say that in public.
Yeah.
People are still alive, but I was told those things.
Yeah.
I was told those things. And there are good people. There are people that I actually respect in many other ways, right? But that is the entrenched. That was the, and to some extent it still is, the entrenched opinion. And actually, I should say, in many ways they were right. This was not the easy task. Yes, it would have been a lot easier if I had just said, I'm going to hunker down and get a ton of papers quickly out on this stuff. Yes, that would have been, from a very narrow perspective, easy. And so they were not even wrong in a certain way, right? But I don't regret having done what we've done. Now, when I say create spaces, you have to create a lot. If you want to actually have, this is a space like that, creating workshops, creating activities. That talk that was out and I presented was precisely a talk at one of these conferences where I was sort of saying, hey, this stuff matters, right? Some of us were saying this stuff is important. It's very similar to this workshop where we're saying this matters in this context, right? We also had to create a legal framework. So NumFocus is a foundation that we founded in 2012. It's a nonprofit that provides what's called fiscal sponsorship. That's a figure, basically that allows individual projects like IPython, Jupyter, but also Matplotlib, Julia, Pandas, software carpentry, R Open Science, to become part of a 501c3 without each of us having to be our own 501c3. Being a 501c3 is complicated. Right? It has to do with tax code, there's legal implications, it's a ton of paperwork, and if you're trying to build an open source scientific project, spending all of your energy into that legal process is pretty draining and difficult. And so what we did was we founded something that would be an umbrella entity that would allow all these projects to come together. It started in 2012. John was actually one of the founders as we were he was falling ill. But now the foundation has grown a lot. It organizes conferences, it provides fiscal support for all these projects, and it creates a space where these projects together can now work in unison and benefit from each other, support legal resources, fiscal support, and tackle issues like getting funding and resources to not only support the projects, but move the projects in important directions, such as specifically tackling diversity in the space of scientific computing, which is one of the missions of NumFocus explicitly. But I also work at a university, right? I have a dual appointment between LBL and UC Berkeley, and back then, actually in 2013, my appointment was only at Berkeley. And so, again, this stuff is not seen as, this is not what you do as an academic. So, again, try to create spaces, try to push out the boundaries so that you can breathe and so that you sort of have a right to exist. So in 2013, I was lucky enough to participate in a project to create the new Berkeley Institute for Data Science. It was something that came out of a project where two foundations, the Gordon and Betty Moore Foundation of Intel, Gordon Moore, the founder of Intel, and the Alfred P. Sloan Foundation got together and supported 3 universities, Berkeley, NYU, and the University of Washington, Seattle, to create entities for data science, environments for the development of data science. This started in late 2012. Nobody even knew what the word data science was. Buzzword compliant institute, let's call it that. But we did assemble, a lot of people at UC Berkeley came together to try to imagine what it would look like to create a different kind of academic space that would be very open, very collaborative, genuinely interdisciplinary, where all of these principles that I've been talking about would be recognized as first-class citizens and would be embraced rather than tolerated as best as long as you get money and you don't get in the way of other stuff, and you still get it on table. We actually launched it, so this was the meaning of the launch. Some of you may recognize Peter Norvig from Google or Tim O'Reilly, along with people from our campus who participated in that. We put together this idea, and when I say build, I literally mean build. We had to build the thing, we had to design a space. This is, has anybody here been to the Dove Library at UC Berkeley, on the Berkeley campus? So if you ever swing by, you have in that, okay? So if you ever swing by Berkeley, in the main campus library, in the dead middle of campus, it's the old main library, it's called Dove Library. You walk through the door, first door on your left, this is it. We designed it to be a space that would be open, that would be flexible, where community activities could take place, where people could do their individual work, but we could have a lot of different modes of work and research. And it's hard, but it's great. I'm not going to say that everything we've done has been successful. We've made many mistakes along the way. We've learned a lot of lessons, but it is absolutely critical. Spaces like this, like Unfocused, like workshops at conferences are critical if we want to change the context. It's not enough. It's not enough to do only the technical work, as important as that is, and this is why making this kind of change is hard. To do both, right? If you're playing by the rules, the system works to your advantage. Everything's already set up, and all you have to do is check the boxes, right? If you're trying to create a different space, you have to do both. So you have to be twice as good, and you have to do double work. It is the challenge that we have to face, unfortunately. So I want to interweave kind of this context and these motivations with the actual technical work. As I said, you have to do both, right? It's not enough to do only one or the other. So I was mentioning sort of this idea of interactivity and of exploring your own data and of being able to run code and visualize data. This is sort of from experience, what the life cycle work, regardless of your discipline, tends to be. It's a cartoon, it's a little bit schematic, but I don't think it's completely incorrect to say that a lot of what probably many of you in the audience do looks a little bit like that. You do some work on your own, at some point you collaborate with a colleague, you may send them some scripts by email. I mean, these days, people do have better and better practices, but it used to be that basically this was in MATLAB, and then you would email them scripts back and forth, and then you would write the MATLAB prototype in C, and then you would copy and paste all the figures generated from the MATLAB screenshots into Microsoft Word for a manuscript, and then you would copy and paste them again into PowerPoint for slides. And God forbid reviewer number 3 asks you to change some parameters and rerun something because you have no idea, right, where that screenshot came from, when it was taken, where the code was, which version, etc. Right? So we try to think that this is actually one problem. This is the life cycle of computational research, and we should think of tools and processes where you can move fluidly back and forth along this way. We're making a change here that's trivial as going and changing parameters and recreating the pipeline all the way and having the figures where you can take the environment where you're coding and you work in that environment in an educational context and teach with it, where all of this is just one problem. Because data science, scientific computing, whichever flavor of the spectrum between algorithms and simulation and analysis you happen to live in, is fundamentally, I think, two classes of conversations that happen sort of at the same time. They happen sort of in parallel. On the one hand, you have a dialogue between yourself and the computer. The computer is your partner in trying to understand a problem, and trying to understand your data, and trying to design your algorithm, and trying to optimize it, but you're basically using the computer as a partner to help you extract insight and understanding what we've done is basically we've built tools, we've built protocols to communicate between the actions of the human and what the machine can do to represent what's happening in that process, to capture it. We've built user interfaces that we try to build to represent the best patterns in those workflows for that to be effective. But there's also a conversation among humans, because the actual purpose of all of this work is for you to present your results to your colleagues at a conference, to write a paper, to teach. Output is going to be often meant for humans as papers, as books, as blogs, etc. And so we've also tried to imagine how can we build narratives, stories that weave the computation very seamlessly into the process. And for that, we've had to build architecture that is more centered around formats, around archival capabilities, around transformation capabilities, and services. So this project that started as a grad student fooling around alone, messing with the time of their advisor, has become really about building protocols, about building architectures, about building UI, about thinking about archival formats for scientific research, services for the community to work with. And most importantly, that lone person is no more, right? None of what we have done in the project, none of the value of Python and Jupyter would exist if it wasn't because now we are a community of people, and 99.9% of the hard work is not done by me. And I really mean that. All of the credit goes to all of these people who work together in the project, and it's very important that in these contexts, we emphasize that, because the academic culture is very, very toxically driven towards the hero of the PI, the hero of the first author, of the senior author, etc. And I think that's fundamentally a problem. And it's a problem that we need to attack every day, because it's very easy to call that into that happen. So these are the people who do all of the hard work. They contribute in many different ways. There are people in that picture. Jess Henrik is a grad student at Berkeley. Brian Granger, who's one of my oldest partners in the project, is a professor at Cal Poly. Sylvain Paulet is from industry. He's at Bloomberg Analytics. Jason used to be a mathematician who is now at Bloomberg. Damian Avila is an engineer who works for a US company but lives in Argentina and works from Argentina. So we have people here who come from multiple different backgrounds, from industry, from academia, from national labs. Shreyas is an LBL scientist. This picture is taken at the new computing building at LBL where I work. And really, that is the only way that these things happen. It is not the hero PI who makes anything happen at this point. And I really want to emphasize that. And these partnerships are not just with people, they're also with institutions. We've been very, very lucky to get support for the project. At this point, this is a project that cannot run just as a volunteer operation. It's just too big and too complicated. So we have support from foundations, and we also have support from these companies which are putting in resources either in the form of cash or in the form of engineers, in the form of their teams working hand in hand with our team, as I said here, peers from IBM, Google, Bloomberg, Continuum. So we have, there are a lot of people there from industry as well, in addition to the people from academia. And so what happened was that early idea of building an interactive environment in Python, gradually over 10 years, by the hard work of all these other people, not of me, evolved into something that we put out, whose first version we put out in 2011, called the Python Notebook, which was basically the same interactive experience of typing some code and getting some plots, but now captured in a web browser. Who here has used the Notebook? Okay, probably a bit more than half the audience. So for those of you who haven't, you can think of it basically like Google Docs. It's a document editor through the browser, but with a catch. Instead of only text and being able to paste figures, you can also execute code. And that code at first was in Python, and now we'll get to that in a minute. It's more than that now. But now it lets you combine, and we'll go back to this idea that I was trying to describe earlier of weaving the two conversations together, right? Here, I'm talking to the computer, and the computer is giving me a result. But I'm recording that in a document that also has English language and that I can share with you as a notebook or as a web page or as a PDF. And over time, what happened was this led to the project evolving from what we call Python into what we call Project Jupyter. I'm going to cut the story a little bit short in the interest of time. But basically, we looked at what we had been building. We have been abstracting the notion of working interactively, right? Typing code out of terminal and getting answers back. Gradually, we have been building more and more tools, and some of them were, yes, the shell at the terminal, code to execute that over the network to talk to this notebook. But we had also built the protocol, the wire protocol, right? That connected the web browser to that execution process. In addition to the web notebook, we had other clients. We had a graphical console as well and other things. All of these tools that would take those notebooks and make web pages, PDFs, etc. Well, this stuff on the right really had nothing that was Python specific. There's nothing really about Python in any of these things. It's the web browser. It doesn't know. Python is way back. It's where you run the code. So what we said was we kind of cut a line through the middle, and we literally took the IPython repository and split it in two. And a piece of it stayed, and it's still called IPython, and IPython continues to exist. But IPython now is the Python-focused part of this project. And the rest of it became called Jupyter. And the reason was really that all of these tools that could work in other languages, we were making them work in other languages. So we had worked with the Julia team in building Julia support. Who here has used Julia? Fury. So Julia is a really interesting language that came out of MIT a few years ago. It's sort of an evolution of many of the ideas from MATLAB, from Python, from Ruby, from R, in a very modern language, focused on numerical computing, fantastic, really talented team. We had worked with them. We also had our support. Support was going for other languages. But obviously the Julia people didn't want to be running IPython. The R people didn't want to be running IPython. They wanted to be running something for R, something for Julia. And architecturally, it was. So we renamed it. And so that's kind of the story between the split. And so IPython, in a sense, spawned a parent, right? It spawned a project that was really the parent umbrella. And IPython shrank into being the piece that is Python specific. The protocol in Jupyter, in the architecture, is agnostic. Python is kind of our anchor, obviously. But as I said, we support Julia, we support R. The name Jupyter is not an acronym, but it's kind of inspired by Julia, Python, and R, right? Which are the three open languages of data science, is the way I like to call them. But it supports many more. I mean, Scala, Perl, Ruby, Go, Haskell, you name it. I think there's over 50 or 60 languages supported at this point. Anyone can implement that protocol. It's a protocol, right? And you can implement it with any language in the back end. To give you kind of an idea of technically the structure, I think it's useful to have an analogy with the web that we're all familiar with. What is kind of, in a very simplistic fashion, how is your web put together? There's a protocol, there's the HTTP protocol at the bottom, right? Which is a well-specified protocol. There's servers and there's clients, and they speak over that protocol. Now, the clients are typically browsers. They don't have to be browsers, right? You can request data over HTTP with wget or curl at the command line. You can build services that speak something else using HTTP as a transport, right? So the client doesn't have to be a browser. The browser happens to be the most common one. Now, if that traffic is traffic that you want to represent as a document, if you want to capture that in a document that you render, then the format for that capture, the natural format is HTML, right? Which is what you use to then render that. And so these two ideas, we sort of have a similar analogy and a similar breakdown. The protocol, which is what you send over the wire to execute the code and get the results back, is our Jupyter Interactive Computing Protocol. We don't have a nice acronym for it. It's basically JSON packets traveling over the wire in a well-specified format, sent by, transported over ZeroMQ connection. ZeroMQ is a networking library written in C++, but that has bindings for just about anything under the sun. So it's very easy to write clients for it because just about every programming language these days has ZeroMQ bindings, except the Node ones are kind of messy, but they're working on it. And then, if you decide that that traffic is something that you want to turn into a document, then there's a document format. There's a notebook, right? But just like with the web, we do have services that use the protocol that are not notebooks, right? The notebook, the architecture goes deeper and can be the Lego blocks, if you will, of the architecture can be recomposed and reassembled in different ways. The protocol is basically supercharging the P in REPL. REPL is an acronym that stands for Read, Eval, Print, Loop. It's a common acronym in the CS world. Many of you, I'm sure, are familiar with it. And it's basically what we have in all manner of interactive shells. It reads input, it evaluates the input. P is as in print, because typically REPL just print the output, and then it just loops, right? What we've done is sort of put the P on steroids, and rather than just print output, we represent output in a variety of ways, and we've kind of abstracted over what displaying output should be. And so we can represent text, yes, you can print, just like in the shell. But the output of a command could be itself a figure. So instead of plain text, what we do is the encoding of the output is actually a JSON dictionary keyed by MIME types. So anything that is about that MIME type can be represented as output, whereas in traditional REPLs, it's basically the old Unix model is standard output is just text, right? So it's a stream of text. That's what standard, and processes have two streams, standard out and standard error. Instead of that, what we have is a table of keyed by MIME type that you can publish output on any of those channels, which means you can represent images, you can represent mathematics, and render mathematics as a first-class object because we think it's important to represent math well for scientific activity. And because we're building a client in the web and all of this stuff is on JSON and whatnot, we made HTML and JavaScript things that we recognize first class. That's what web browsers are good at, right? But we also can return output, which is actually full-blown interactive stuff. So, because remember, now you're rendering output, but that output is connected to a process in the back. And so, and you're rendering it typically in the context of something as nice as a web browser that has lots of interactive control and sophistication. So we've made that also a first-class citizen of the protocol so that you can actually, with one line of code, take a piece of computation and simply say, I want to interact with it and have it automatically become an interactive control to explore the parameters of the model, for example. Now, that was the protocol. The counterpart, the format, is the notebook, the document, right? And the notebook is a sequence of cells. So you have a cell with you have cells with text and cells with code. A text cell is Markdown and LaTeX. So you type Markdown and you can have also LaTeX in it. A code cell is code in a language, and when it's executed, the output that I just described. There's metadata everywhere. Each of these cells has a little JSON post-it note, if you will, attached to it. So that can inject metadata everywhere in the notebook. And there's metadata at the top level, at the notebook itself, and at the cell level, and at the output level. And there's multiple projects that make all kinds of interesting uses of that metadata to process, transform, and understand what the notebooks are. The underlying format is JSON, which is kind of reasonably plain texty. The schema that we use is publicly documented, so that it can validate a document. It's meant to be, because it's JSON, it's also a data structure. It's machine readable, so it's easy to write tools that work with it, right? You're not parsing logic for crying out loud. You have a data structure where these days just about every language has a JSON parser. And in Python, we provide actually an API so that you don't even have to work at a JSON schema level. We just give you an API that says, give me a notebook, give me a new cell, and lets you work grammatically. And we have tools to transform it to many other formats. Because it is a data structure and it's well documented, we have to give you the tools so that you can say, I need an HTML version of this thing, I need a PDF version, and I need to customize how I get my HTML to do all that.
Is it interchangeable with LaTeX? Like, can you create a LaTeX document?
Yeah, export. So ND-convert, this tool has export to LaTeX. So you can say ND-convert -- to LaTeX. And you'll get a LaTeX version. We provide a default template, but if you need a highly customized LaTeX output, then the conversion process is based on a Jinja template machinery. And you can provide your own template to say, this is how I need the LaTeX to be produced. And I do have that stuff. I mean, it works. There's a lot of corner cases and weirdness here and there. I have a postdoc who's starting to work right now, who's going to basically spend most of his time working on that part of the project, you know, the publishing and document pipeline aspect of it.
Because, I mean, given where we're at, the ability to turn such a nice, beautiful thing into a paper context would be
So yeah, there is conversion, and I'm happy we have a workshop this afternoon. I'm going to be here all day, so I'm more than happy to dig with you into the code and show you the technical details and look at that as much as you want. So this has become sort of a large ecosystem. As I said earlier, if we wanted to have this something that would become widely adopted, then we would have to build services, not just the tools, but actually services to help people. And so Matthias, who's now a postdoc with me and was grad student when he did this, actually said, well, we have this tool that you just asked about to convert to LaTeX and HTML, but people have to have it installed. What if somebody wants to share, if you want to share with a colleague a notebook, You'd have to send them the notebook, and they're going to say, what is this thing? I open it, it's a bunch of brackets. I don't have this thing installed. If you make me install all this stuff that you like, I don't have the time for it. They're going to say no. If you could send them a link and say, hey, click on this link. And when they click on that link, that's it, just opens on the web browser and they can see it. Then they might, that might be all you need, because all you might need their feedback on that, and there's enough information and text and graphics in there that might be enough for what you need from them. Or if you actually need that to work, that probably might be a good way to hook them in and say, oh, this actually looks really interesting. Let me now go through the effort of installing this thing that you want me to install, actually use it, right? And so that's what MBViewer is. It's a web service that simply allows you to paste in the URL or GitHub repo of any notebook anywhere on the internet, and it renders it into an HTML page. And so that is a lot less critical today, because today GitHub renders notebooks natively. Any notebook stored on GitHub is not naturally rendered. That wasn't true when this started. When this started, notebooks on GitHub would look like just raw JSON. You would see just all the braces, right? So it was really annoying. And one of the things that we want to support with this is the idea of reproducibility in scientific research, of making it possible to really build upon the work of others. So this is an example of a paper that we wrote in 2012 with some of the i5 Jupyter group and microbiologists from the University of Colorado who are now at UCSD. And we wrote a paper. We took some total genomic analysis code that they had, poured it on Amazon in the cloud, and collaboratively worked into turning the code into notebooks that would then use the i5 parallel machinery to parallelize and run the analysis much faster. This was done starting at between 9 a.m. and 2 p.m. at a conference, because I had to give the demo at 4 p.m. and we started in the morning. And the funny thing is, we literally started trying to hack out a quick example in the morning, and by 2 p.m., he said, oh, actually, we've got a really interesting result. Let me call the editor of this journal and we'll publish this while you present. That doesn't normally happen to me, but hey, I'll take the wins when they happen. But what we did was not just publish the paper, but we actually published the notebooks that went along that created the results in the paper in a website that had, you can't really read it here, but the point is here, there's an Amazon machine image identifier. So that if you care about this topic, you can go to Amazon with your Amazon credentials. The one thing we don't do is we don't pay for it for the runtime. But you can go to Amazon, punch in .ami ID, and you will effectively boot into the paper. You will boot into the paper with all the data, with all the code, with all the dependencies, and you can run the analysis. And if this kind of research is something that is relevant to you, that's a hell of a lot easier than going through the effort of installing everything and figuring out what they did, and did they put the code online or not, or blah, 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 blah. You boot into the paper. And then you can choose how much you run it, how much time do you want to spend on it. So this is really the idea of putting in practice something that's a very old code. This is from David Donahoe from Stanford from 1995. David Donahoe is a statistician at Stanford. A lot of effort into thinking about the problem of reproducibility in scientific research. And he said this in 95, which I believe is really, really true, and I think it's a really important quote. Because we're so obsessed, and so much of our culture is focused on the credit of the paper. And what Donahoe said was the paper is not the real scholarship. It's not the real work. The real work that matters is anything else that will come with the paper. It's the code, the data, the environment, so that you can actually build on top of it. Because these days it's rare that just by reading a paper you can actually do anything.
This culture is starting to change. I mean, like the PL community is already taken. Well, you probably know this, but I don't know.
No, please.
Yeah, so I mean, the PL community is already put in place like a very strong artifact structure, so that people can upload their code, upload their data, and upload these virtual environments, and then other people will review it and will give them like a badge of honor, like we have all our code is reproducible and so on. And now ACM is actually encouraging other SIGs to adopt similar methods. So like at SIG-IR, we just had this discussion in Italy 2 weeks ago about how and when can we start adopting this type of models. That's amazing. I mean, this is like really powerful.
Yes, it's been 20 years in the making. It's fantastic to know this. The battle has been long and hard. When we did this in 2012, I was still giving talks about reproducible research. People were like,
the winds are changing.
The winds are changing. I'm actually part of the ACM advisory committee on that, and it's fantastic to see that this is changing. But it has been a long road. Donahoe said this in '95, and it made sense in '95. I mean, we haven't fundamentally understood anything that was confusing about the statement in the last 20 years. It has just taken 20 years to both build the technical tools to make that easier and to change the culture. And the second is far more important than the first, because it really has been that cultural battle of changing what is considered acceptable in communities, right? And that idea of changing what is considered acceptable in the community applies as much to reproducible research as it applies to questions like the ones that are being addressed in this work.
So is this already an affordance of Jupyter? Is this already something you can do in Jupyter? Is it something you hope to add, or is it a functionality that already exists?
I'm not paying her to ask these questions. I promise.
You didn't even tell me to.
So, this is an example of a paper from Nature, a Nature genetics paper, not by us, right? It's one thing if you do something about yourself, right? Yeah, of course, right? You're touting your own horn and you're telling the world how good your stuff is. If someone else actually says, this is how it will work, that's a different signal. So this is a Nature genetics paper about head and neck cancer. I'm not a medical doctor, I have no idea. I hope the paper is any good. Willing to trust that the paper is any good, a little bit more, not because it was published in Nature, but because they did this. The paper is their advertisement. It's the sales pamphlet. They did exactly what Donovo said, and they put a GitHub repo that has 20 notebooks, not one, 20 notebooks, replicating every table, figure, number, every single last result of the paper is actually expanded and replicated in these notebooks, and it's all up on GitHub. Yes, please.
So I was going to say, I just went to a reproducibility workshop at Penn State,
Mhm.
but and they're doing the Galaxy days that links into Jupyter.
Mhm.
But I think that they're funded by NIH
Mhm.
to do this project, and so I think it's going out not just to the computer science community, but to researchers, so it's still like way down end users. It's not just people who are developing something.
Mhm.
So I think that's really exciting.
Yeah, that's a very good point, and it's a change that has been a long time in the making, but it is happening. An important driver at NIH is Phil Bourne. So Phil Bourne, who is the associate director for data at NIH, which is a very high-level position, is a huge, huge advocate of these ideas and has been so for years. But now that he's in a position of a fairly high authority, he's been pushing programs in that direction. And the federal agencies are becoming increasingly kind of stern in their mandates about sharing reproducibility and openness. And we want to play a part in that, and hopefully we're helping. So does this answer your question?
Yes, it does. One more just follow-up, because I'm tweeting as you're talking, so I want to make sure I'm tweeting the right things. Is this part of Jupyter? This is officially part of Jupyter to include the notebooks? Not this paper, obviously, but the ability to share the notebooks. Oh, you're saying they're shared in GitHub, but
Yeah,
they're notebooks. They're Jupyter notebooks that reproduce how they got the tables and so on.
Yes, but I mean, in a sense, we make it possible that they do.
Right, no, I get
kind of
it, but I'm just saying, like, if we want to spread the word and say this is what you should be using, the link should be to Jupyter, to Project Jupyter.
Yeah, that's probably a good starting point.
Thanks.
And this is actually something that is relevant to this discussion, which is the next step. So I showed you how in 2012, we put together an Amazon machine image, and it's a VM, and it's kind of clunky and complicated. You have to know how to assemble a VM. I didn't do it. Now, Jeremy Freeman, who's a neuroscientist at Genelia Farm, put together this project called MyBinder. What is MyBinder? MyBinder gives you one line. It's one text box. You click in the name of your repository. And if your repository on GitHub was assembled with the right pattern, basically he tells you how, the project tells you how. If you provide what are the dependencies or a Docker file, what Binder does is automatically it creates a Docker container that is ready to run with all of them, all the code, all the dependencies, and the notebook ready to plug in one click. So literally, all you have to do is say, my repo follows this pattern, please make me a binder. And here you go, there's your binder. So what took several of us a bunch of elbow grease frantically for a day, and people who really knew what they were doing with Amazon and whatnot at the time in 2012, now is literally follow the standard click. And he pays for it, by the way. He pays for the runtime. So he's out of his grant. He keeps a fleet of 800 nodes on Google Compute Engine that are ready for you, ready to run.
Who is he?
Jeremy Freeman.
Okay.
From Genelia Farm. He's a neuroscientist at Genelia Farm, which is a Howard Hughes Medical Institute research facility in Virginia. Fantastic guy. And Andrew Osheroff from his team is the person who has done the bulk of the development of the technical work on Binder. There's a great talk from the recent sci-fi conference a few weeks ago in Austin where Andrew presents kind of the project and the architecture. So we started at microbes, but I want to talk about black holes for a second, because we're doing this for science, right? We're doing all of these things. I started as a physicist these days. I'm probably the closest thing professionally that would describe me as kind of an applied computer scientist in some sense, data scientist in this community. But I don't forget that whatever tools I build in the computational sense have to help people solve problems. And a very long time in a galaxy far, far away this happened. This is a cartoon of two black holes spiraling into each other. So two black holes spiraled into each other, and Einstein in 1915 predicted that if this were to happen, we should be able to see it because it would send ripples in space-time that we would see as gravitational waves. So light is a wave, right? This laser pointer, this light is a wave that travels, but it's a wave where what oscillates, what moves up and down, are the amplitudes of electric and magnetic fields in space. That's what light is. It's the oscillation of electric and magnetic fields, and whether it's green light or whether it's the radio frequencies that cell phone use, it's all the same. It's electric and magnetic fields oscillate. Gravitational waves are different. When masses move, space and time themselves stretch. So they're kind of tricky to detect because we don't see them. It's space itself which is changing. And so not only is it space itself, which makes it complicated, they're also really, really tiny. So in order to see these things that were predicted by Einstein's equations in 1915, people have been building something called LIGO, the Laser Interferometry Gravitational Wave Observatory. LIGO is a set of two facilities, one in Washington, in Hanford, and one in Louisiana, in Livingston, Louisiana. These two things are separated by about 3,000 kilometers. Each of these things, L-shaped device that has arms that are about 4 kilometers each, so huge arms, right? And it's called an interferometer. So what you do is the following. These two arms are high vacuum arms, and at the junction, there's a laser. And there's a device called a beam splitter that takes that laser light like this and splits it and sends half of it down one arm and half of it down the other. At the end of each arm, there's a mirror. It bounces back and forth. So what happens is because it's the same light that is being split, and the arms are the same length, it goes down, comes back at the exact same time. What happens is space stretches, right? One of the arms gets a little bit longer and the other one gets a little bit shorter, right? Space is like a rubber sheet. And so space itself changes, the two arms get offset, and the waves don't come back exactly in time and they get offset. And you see that as a pattern of interference. That's why it's called an interferometer. The problem is that pattern is teeny. So the sensitivity that this device has to achieve is about 21 orders of magnitude. To give you an idea of how hard that is, let's put it in imaging terms. Let's imagine that you're trying to detect an image of an object roughly the size of a human being, of a person, a meter or so, a meter, 2 meters, right? Order of magnitude. In a larger image that is not the size of this room, that is not the size of the building, that is not the size of San Francisco, that is not the size of planet Earth, that is not the size of the solar system, but that is the size of the galaxy. You have to find one person in a picture the size of the galaxy. That's how hard measuring 21 orders of magnitude is experimental. And it's a feat of engineering. These people have been working on this project for 30 years or so. I saw one of the early talks when I was in grad school when they were assembling. They hadn't even put it together, they hadn't even come online. And I basically thought, okay, these people are lunatics. Can't do that. Like, you can't. You just cannot measure a distance which is 1,000th the radius of a proton over 4 kilometers. Because literally, quite literally, the waves crashing in the ocean in Louisiana create a larger signal than what they're trying to measure. A truck going down the highway miles away creates a bigger signal than what they're trying to measure. So this thing is an insanely complicated combination of engineering and data analysis to filter out everything. And in September 14, 2015, They saw it. Two black holes, 1.3 billion light years away, collided, and they generated these two signals. By the way, why do we have two? Why not just one of these? You can think why we need two of these devices instead of just one.
If this is so hard to measure, it would be easy to have a correct result.
Exactly. Exactly. To decorrelate spurious signals. It's exactly that. Because a person, somebody coughs near the experiment, any of those will create a signal. But that signal, if it's really a truck, won't appear 3,000 kilometers away, right? So you need two of them to basically sort out false positives.
But wasn't there also some, sorry, this
Yeah.
is, my neighbor downstairs is an astronomer, so I happen to have heard a little bit about this. Wasn't there some crazy story that like they turned it on and then like a wave appeared something like 8 hours later, and they were so shocked because the expectation was that this would happen like once in 10 years or less.
Technically, it wasn't on. So technically, you're right, and technically it wasn't even on. It was in what's called engineering mode, meaning they hadn't officially started collating data. They were going to start like 3 days later. But
And
the
if they
machine was
had
on.
waited 3 days, they would have missed it.
Well, no, so the machine was on because in engineering mode, it was already, they were doing the final testing, but they hadn't sort of said, okay, we're live.
Right.
But the machine was ready. Now, what happened was that day, they were thinking about running a test.
Right.
And if they had run the test, they would have missed the signal because the test would have messed up with the machine, and they were still not officially on.
And somewhere in the multiverse, there's another universe where they ran the test. And they couldn't find a way.
Yeah, what happened was, this was the story
Just
told
mind them.
by Dan Holtz, one of the project leads, and he was telling the story at LBL in February, presenting that plot, where he was basically saying, it got late at night. You know, like, let's run the test tomorrow. And they got a signal that was perfect. So this is beautiful. This is the signal in Washington. This is the signal in Louisiana. They overlap basically perfectly. This is the signal at the bottom, is the signal from a purely numerical simulation of that event. And you can see, and these are the residuals from subtracting the numerical simulation from the real world data. It's basically the cleanest thing they could have ever imagined. And by the way, all of these plots, Matplotlib. That little library that John started back in 2001 to share his EEG research openly with the world is now the library that is powering. This is probably going to be one of the most cited papers in the next 100 years in physics. It's kind of a seminal discovery in physics. And it was done with these open tools. This would have been done with proprietary tools 10 years ago, no doubt about it. It was presented at LBL at one of the most exciting talks that I've ever seen in my life. It was kind of standing room only. The Q&A went on for 45 minutes and they had to stop it.
I mean, you should go back to the picture.
Sure. And the LIGO project put things openly in their Open Science Center as Jupyter notebooks. So they actually release all of their analysis as Jupyter notebooks, and using Binder, you can run it. In fact, at first, Min, who's one of the senior developers in our project, made the binder so that you could not even have to download the notebooks, but actually just click on the binder link and run it yourself. And the LIGO project seemed to have liked that. And now, if you go to their official website, now for every new data release, they make the binder link themselves. So now they are making this. So the binder that I talked about, now it's officially, if you go to the LIGO Open Science Center, it's right there. And remember how I said, well, we made the protocols in Jupyter able to not just remember that P star, the print on steroids. It's printing that out, but it's also representing any output of any computation. Well, what better way of representing the result of computation, which is a wave, than sound? So you can take a computational object and display it as audio using our protocol, and we're taking advantage of the fact that web browsers are pretty good at displaying video and audio and whatnot. And that whoop at the end, that is the sound of two black holes running into each other 1.3 billion light years away. That's exactly what they sound like when they start oscillating. They go faster and faster and faster, and then they merge and they stop sounding. That's why the frequency goes up. That's why it sounds like whoop, a chirp. Because as they spiral, they go faster and faster and faster, and then they collide, and then they quickly, it's a thick medium, once they collide, it just stops. But that's the run-up to.
Wait. Okay, one more time. Never mind.
You can go to Binder.
Yeah, no.
You can run it. So we are trying to use these tools to actually change the scientific culture. This is an example of a project we did in 2014 with Nature, where they wrote an article about using notebooks to share your code with the community. But in addition to that, we actually put a demo on the Nature website. We put a demo running notebooks hosted with basically the predecessor to, or one of the building blocks of Binder. So we were basically using temporarily online hosted notebooks. In this case, to show that you could have scientific results hosted on a publication like Nature. Now, this was not a paper, we just wrote a demo using openly available data. In this case, a demo of interactively exploring the Hubble deep field image, which is a classic image from the Hubble telescope, and doing galaxy detection by changing the thresholding of the image processing algorithm. But the point that we were trying to make was it's possible to host live papers, live executable papers, even by a journal, if they want to do this. Now we're technically at a point where this is not a mirage anymore. Books can be made executable. This is an example of a Springer hardcover, nice glossy paper book from Springer on signal processing that was written as, you can buy it from Amazon, you'll get it, it's nice and expensive, but you can just clone the repository from GitHub, and it's a collection of Jupyter notebooks so that you can execute the book yourself. And so you don't have to wonder whether the author copy-pasted right, whether they have to make files right, whether the version that's in the book is different from what's actually available in the zip file. No, you're actually effectively running the book yourself. We've now built other machinery on this infrastructure. Jupyter Hub is something that allows you to deploy Jupyter, the Jupyter environment, in a large organization, whether it's, or not in an organization, let's say. Whether by organization, you mean your research group, where you work, where it's you and 4 other people, and you just have accounts on one beefy computer where everybody has an account, or literally a huge organization. So for example, at UC Berkeley, this is being used now to host the new curriculum in data science that Berkeley is developing. Berkeley has a big initiative in data science, and in particular, there's a course, it's a beautiful textbook. It's all online, called Foundations of Data Science. What's that?
And it's called what?
Foundations of Data Science.
No,
the book is called
the tool.
Jupyter Hub.
Jupyter Hub,
I'm sorry.
Oh,
Jupyter Hub.
thanks.
And the book is on GitHub. You can clone the book, you can see it, but it's a book that basically attempts to tackle the problem of teaching many of the ideas that are relevant to this conference about inference and computation to potentially all incoming majors. So the idea was, how can you, if we're going to think an educated citizen in 2020 in society should understand how to reason about data, then we have to present those ideas in a way that doesn't require everyone to become a computer scientist. Because theater majors also need to understand something about data that may impact public policy, that may impact their taxes, that may impact other areas of their life. But we don't need theater majors to become computer scientists. So how can we present to many disciplines that are not traditionally mathematical and computational these ideas in a way that is rigorous and sensible and accessible? So Berkeley has been developing this course called Foundations of Data Science. The website for that, the hosted version is data8.org, and the book is at inferentialthinking.com, that takes Jupyter notebooks and explains the concepts, and with very, very small amounts of code, builds the ideas of inference, analysis, and statistical reasoning around data without having to build upfront all the mathematical machine. And then there are elective courses later that attach to this course that go in a variety of directions. So if you are interested in the mathematics, you can take a course on statistical foundations. If you're interested more on the algorithm side, you're more a CS person, there's a course on algorithms and data structure. But if you're interested instead in ethics and the ethics of data, there's a course called Ethics and Data. If you're interested in neuroscience, there's a course called Data in the Mind. And so there's a collection of courses that now take that foundational idea and take it in multiple directions to try to serve the whole population of campus. And this is hosted. When students click here on Interact, what they're taken to is a Jupyter Hub, one of these Jupyter Hub instances, which is hosted on cloud servers for campus students. So this has now really become sort of infrastructure. I was showing you the one from Berkeley because we run it for our students. Companies are using this, so this is an example of Microsoft deploying notebooks for machine learning in the Azure cloud. IBM has a version called the Data Science Workbench. Continuum Analytics has a version hosted in the cloud on Anaconda. Google has something called the Cloud Data Lab, which is basically Jupyter Notebooks hosted in the Google cloud. So you can pick the Microsoft cloud, the Google cloud, the IBM cloud, Continuum cloud, and each of them obviously offers differences in pricing and differences in data services that they offer and UI. But fundamentally, you're still sharing the same environment and the same notebooks and the same class of work with these ideas. Another company that is using this is O'Reilly, where remember how we said it's not just the notebooks, it's actually the underlying protocols. So what O'Reilly did was they said, well, this is a great way of delivering computational content to our audience. Because these days they don't just sell paper books, even though their paper books are great and they're cute and they have cool annual covers. So what they've done is they've basically torn apart the infrastructure of Jupyter and said, we're going to run the kernels as a service, the backend that executes the code, and we're going to allow that to attach to any web property that we have. So if you go to an O'Reilly website, now you can have, this is not a notebook, this is just a website, and it has a run button, and when you click it, the code actually runs. And you can actually even edit it. So now they can offer all of their online material backed by the Jupyter architecture. Even though it's not running our version of the notebook, it really is using the underlying protocols and architecture. And after they did that, they developed something new that they launched a few months ago called Oriole at O'Reilly, which is an educational initiative to deliver tutorials online that combine the notebook, the computational narrative with live human narratives. So this is an example of Oriole that is a great illustration. So Peter Norvig, who's the head of research at Google, I'm sure many of you have read his works, often blogs, and his blogs are just notebooks. He literally just types up a notebook and puts up a link to NBViewer. He doesn't even bother sort of creating a separate blog. He just points to NBViewer. And his blogs are these delightful, his blog posts are these delightful analyses of computational questions, where he walks you through a problem. He takes a problem and writes a little bit of code, thinks about it and explains what it means, and then says, okay, now let's do this other little thing. And so there are these very engaging walkthroughs through problems in computing and data that are absolutely fascinating. This is an example that had a huge amount of traffic. We know when he posts because we see the spike. The spikes in traffic. Right? He generates in 24 hours our normal traffic per month on NBViewer. And so this was an example of finding the shortest regular expression that would match all the winning presidents of US elections in history and not match those who didn't. It got a lot of traffic, it was based on an XKCD comic. What Oriole is, it takes that notebook, but actually gives you a live video of him narrating the story, and the live video is time synced to the segment in the notebook with a live table of content. So you can actually watch the video, and as the video plays, you can follow up. But if you skip back and forth in the notebook, if you move back and forth, the video follows you. So you basically have Peter himself explaining to you and narrating kind of the ideas behind this. So this is a platform for delivering content that they've created using the open formats and their own stuff. So I want to close kind of the technical part with a little bit of what's happening next in the project. So, yes.
Can I ask a question, Fernando?
Yeah.
Can I do the same? For example, say I have code that I want to share with my friends. I have access to external host. People can actually make a link to that post. Can I have the same? People can run my code and the results in the one browser.
So with Binder, you can. The only catch with Binder is the easiest way to do that, I would say, or one of the easiest ways these days, is Binder. Binder allows you to do that. The only catch with Binder is that Jeremy has a limited number of hosts, and so they may be full. So it's kind of a best effort service because he's literally paying for it out of his grants. But Binder makes that very easy. I think Microsoft has also a service called notebooks.azure.com. Which also I think has a free tier, if I remember correctly. And so you can host the same idea. You can host the node, basically put a version of the notebooks there, and anyone who people can log in. The difference is that on the Azure one, people have to log in, whereas Binder is no login. It's completely anonymous. Basically, you click on the Binder link, Jeremy makes a copy, spawns that Docker container. As long as you're connected, you can run, and when you log out, it gets destroyed.
Say I have my own host. my own machine.
Yeah. Oh, okay, I misunderstood the question. If you have your own machine, then yes, Jupyter Hub is the best way to do that. Jupyter Hub allows you to give people accounts, you can authenticate. So that's what we're using at Berkeley. Literally, that's how this course is taught, right? The materials that GitHub repo and the students come in, they get their own copy, right? And from their copy, they can use it themselves. So, and so yes, I'm sorry, I misunderstood the question. So where are we headed next? With all of this, there's a lot going on. I'm just going to focus on one small piece of the project, so we wrap it up. I'm already way over time, I'm sorry. So what we call the notebook is an environment that has notebooks that we've seen already, but it also has files because you have to be able to access your notebooks. We also have a terminal emulator in there. You can actually access a regular terminal where you can run VI, Linux, and any terminal process. We also have a text editor in there where you can edit normal text, Python, whatever. Process manager so that you know which kernels and which notebooks and which terminals are running. We even have a cluster manager for the parallel stuff that I mentioned before. So the word notebook is really a misnomer. This is becoming a platform with lots of services for computing. So we kind of understood and embraced that lesson that all these things were needed. And instead, we put them together in a platform that really makes all of these things work together much more seamlessly, rather than keeping like, okay, now we need this, and now we need that, keep adding another tab to the system. We've been closely working with Continuum Analytics and Bloomberg, and with the support from our foundations, into a new architecture called Jupyter Lab, which is the same notebooks and the same services, but now in an environment where they can live on the page wherever you want them to be. You can put them next to each other. They can talk to each other. The web architecture is designed as plugins. So now literally Jupyter Lab is the environment that offers all of these, but the notebooks, and this is now a graphical console where you can run code, but it's not a document. It's like a console, like a terminal, but with all of the built-in interactive features, but for basically non-permanent work. You can have a terminal. You can also have a text editor right there. You can have a markdown render, and each one of these tools is a plugin. So now we provide the basic set of plugins. There's APIs for them to talk to each other, and you can build new plugins. So if you say, oh, I have this great idea where I want to build something that uses this architecture, uses these sparkles, but represents my data, does whatever I want in my context, you just need to add another plugin to the system. And so this is kind of where the environment on the technical front, one of the directions where we're going. And so to wrap up what became a longer talk than I should have had, I'm sorry, I apologize for that. I think it's important to remember that we can create better spaces for all of us, and that is a combination of the technical, the social, and the professional recognition. Because we're not just doing, I would like to think that we're having fun doing this, but we do need to make a living. We want good, rewarding careers for all of us. And so this problem is multi-pronged, and you can't forget one of them. We have to be very, very deliberate and intentional in making sure that as we go along, the communities that we build are actually open and diverse and respectful. That they really allow for ideas to come from many fronts and from people from many different contexts and backgrounds. That is only going to happen if we change the incentive structures, if we reward what we want to build. When you were mentioning that some of these issues in disability are beginning to change, the reason they're actually beginning to change is partly because finally there are incentives that are beginning to do that, right? David Donahoe said that 20 years ago, and nobody listened, right? And he actually published his papers and his books that way. Nobody listened, right? And he was just as right 20 years ago as he is now, but now the incentive structure is actually.
I don't think it's so much like nobody listened, but perhaps nobody was ready, like it was before its time, right? Because it wasn't as easy then as it is now.
Yeah, but.
I mean, I don't know, I wasn't around.
Yeah, no, you're right. No, I think that's a good point. I guess when I say nobody, some people did listen, but.
But it wasn't so easy, I think, then as it is now to make that change and make it obvious.
Yeah.
And now things are starting to shift. I mean, still just starting, but
I do want to emphasize actually that it's the combination of the technical and the social. Because actually the group that David was collaborating with at the time, Don was collaborating with, John Clairbaught's geophysics group, they did have everything automated with what was called Units for Geosciences, I think it was called. And for their research, they had it done and automated. But, so in a sense, for the technology of the time, they have solved the technical problem.
Well, in that one lab.
in that space, but nobody adopted it, and part of it was because the social incentives to do. It was perfectly acceptable to publish papers without doing that, and people could get away with it.
Well, they still can today, but not for much.
We hope.
Well, but I think also there wasn't a lot of research on how little reproducibility
That's right.
there was
How bad the
in
problem
data.
was.
You know, and so
And now
it's
they're
kind of
like-
like a downstream problem. Like if people who are generating data don't have reproducibility, then it has downstream effects for people who are
Right.
using computational approaches to just reanalyze that data, right? And so
Well, and it's for all of science, because you're
It's-
citing papers that are based on faulty conclusions that won't reproduce.
absolutely.
But I also think, the incentive, sorry, this is like, we can take it offline. It's
Okay,
fascinating.
I'm basically wrapping up. I do want you, whenever you try something, think hard. Don't let this stop you, by the way, but keep sustainability in the back of your mind. You shouldn't let it stop you. I say that because actually, if you think too hard about it at the beginning, it paralyzes you. Like, I can't even get started because I don't know how I'm gonna make this sustainable, and you don't even get started. Don't let it paralyze you. But once you begin to pick up momentum, you do have to start thinking about it. Because once things begin to grow, it's easy to crumble under your own weight if you're not intentional about sustainability. And this is really about you. This is about all of you. These things that were built this way, everything that I've shown you was built simply by people who decided not to accept the status quo and who decided to change it. Everything that I've shown you was going against the grain of what the power structures around us were telling us to do. And so it is possible. All of our tools are open source. I would love it if some of you contribute to Jupyter, but you don't have to. You can contribute to anything else. There's a million ways in which you can affect change. But it is possible. And I want to apologize for running so long, but I want to thank you for being patient with me, and I'm happy to talk with you during the break or later during the day. Thank you so much.
So we have some time built in between, we're in our break time, so I think we have time for one question. Thanks for a great talk.
Yeah, and I think we can go a little bit longer. I think the break, since we saw the schedule originally, has changed a little, so the break is now at 10. So we have a bit more time. What I was going to ask is, when something is open source or even source enough, I guess, there tends to be a whole lot of different ways that people take that and extend it. How do you go about sort of dealing with what is promising and you think is going to be really useful, and making that less buggy or more standardized, versus like, how do you just sort through all of the different ways that people try to extend this to make it really better, more widespread?
Yeah, it's an art. And we're imperfect at it. We're very imperfect at it, but we do try to be deliberate in a variety of ways. One is we try to constantly scan the community, listen to the community. We run user surveys on what are the areas that are most important, what are the areas where people have the most need, to try to sort of help and support efforts that go in that direction, while allowing people to explore. Because you always want to, unfortunately now, basically anyone can hop on GitHub and build something new and try something out. We provide communication channels that are very open to encourage that people share what they're doing and explore those directions to see, out of left field, that emerged, and that's great. Maybe that's going to be the next great new idea. But we have activities where we're beginning to have more and more of what we call Jupyter Days, which are kind of local. They're not really conferences. They can be local workshops, community-organized local workshops for people to learn about the tool and share with each other what they are doing. Another mechanism that we use, and this is somewhat specific to industry, is we have a formal incubation organization on GitHub. It's actually called Jupyter-Incubator. It's a top-level org on GitHub. And the purpose of that is to allow projects to kind of formally say, we're going to test this effort out, we're going to see where it goes. And I'd say that it's kind of oriented towards industry because individuals can obviously do that on their GitHub accounts. But often people at companies are told, look, you can't just put random stuff on GitHub on your work time, right? And so by providing a formal organization and a formal process for that, it's easier for teams at companies to say, well, our work is to contribute to this project on the incubator organization. And then what we do is we watch it evolve, we let it, it's being done in the open, we see if the community adopts and embraces it, so that kind of measures the the impact and value, but we also see that the project evolves with the right cultural and technical norms, that the team is responsive to the community, that they handle the community well, that they're open and inclusive, but also that they test things well, that the project is well documented, etc. And if it meets all of those criteria, then we can say, okay, this now gets merged into the main project. And we have had already some tools developed by IBM have gone through the cycle of incubation and then formal adoption. So we have to use kind of a variety of mechanisms to try to tackle that challenge. Yes?
6 months ago, around 6 months ago, I found a fascinating tool. It was called iTorch. It was a little bit hard to install, but it was amazing because I could run all my scripts on Torch to run Tinker and everything. So, and then I thought that was a competition for iPython. I didn't know about it. I saw them there and was surprised. And now I know that for everything. So my question is, is it possible, for example, to have something like iJava? I know people don't use Java.
Yeah. There's a Scala kernel, and
Okay.
Yeah, I mean Java is fairly verbose, and so pure Java tends to be less. I think there is a Java. So iTorch is the Jupyter kernel. It's one of these kernels. One of the 50 or so that I mentioned is the Torch one, which is basically Lua plus the Torch environment from Facebook.
And I think Facebook is doing a lot of that.
Yeah, no, from what I understand, they've done a great job. And so in the Java world, yes, the answer is absolutely. I don't know how good or the state of the raw Java ones is, because I don't do Java, but I do know that the Scala one I think is reasonably good, because Scala, because of Spark and kind of that part of the ecosystem, Scala itself is much more used, and Scala, the language, is a little bit more amenable to interactive usage. So there is a Scala kernel, and in fact, IBM has worked on making sure that the Scala one is well integrated with Spark, so that you can basically run Spark interactively natively in Scala, rather than with one of the language bridges like PySpark, which has a lot of serialization overhead.
A question. So from what you've seen from users, does their typical workflow change? So are people using the notebook as a way to publish their findings, or are they using the notebook as their everyday? Here's how I test out my code and writing my code. So I'm wondering, is it replacing things like IDEs, like Eclipse for developing code, or?
I mean, we don't want to go too deeply into the full-blown IDE space, and the reason is that I think sort of competing head-on with the massive complexity of an idea like Eclipse or Visual Studio is a huge task, and our focus is always sort of Jupyter is already big and complicated enough as it is. We try to find a boundary, and that boundary, we try to say it's wherever you have an interactive component. So but Jupyter Lab has an IDE feel to it already. I mean, you can have, this is a text editor, you can have a console here, you can have debuggers. So Jupyter Lab goes a little bit in that direction, but with the caveat that our focus is these tools, whenever they're connected to interactive kernels and whenever you are kind of exploring, if you're really building a massive library, and you probably want to do that in the best IDE you can find, and we don't need to compete with that. It is being used, though, very widely to share work. I mean, some of the publications that I mentioned, we have a gallery on the website. Let me very quickly show you, as long as I'm still online. So we have on our wiki a page called a gallery of interesting IPython notebooks. I can change the title of the page to say Jupyter, because on GitHub wiki pages, the title of the page is the URL. So if I change this, I'm going to break a million links out there, so I'm stuck. But this has a table of contents of basically materials that are shared in this format, and there's a lot of it. I mean, you can see these are entire books or collections on many topics, and in particular, here's a section on reproducible papers. And so this is a list of academic publications that have been made reproducible in this manner. People publish course materials, so yes, we ran some searches on GitHub, and we know that as of a few months ago, I haven't rerun the search, but as of a few months ago, there were about 500,000 notebooks being shared on GitHub. 500,000. About half of those are public and half of those are private. So about half of that was on public repos and half was on private repos.
That's a great example of impact. So if there's no more questions.
Yes.
There's always.
Let's do it.
So thanks again for an incredible talk. I never knew about this, and I'm really, really glad I do now. I am curious, I mean, obviously the implications for open science are incredible. I'm curious what you think are the implications for like more business/industry. You know, that's something that, I mean, of course, I support FSF, but I also don't think everything should be, you know, free and open software. Well, I saw the page where you said Microsoft Cloud, yeah. But in what sense? Like, here's my question. You're saying, look, this is not a full IDE tool. We're not trying to compete with that. But then again, if you're building anything of scale, anything of serious, you know, level, you need more than just a few lines of code rendered prettily in an interactive SIMI. You need things like Git, you need change, you need the ability to support multiple users, which you are, and you need to be able to support big libraries, which is a little bit more than what you're sort of bringing in. So,
and remember I mentioned, this has been built in a very, very close partnership between our team, Bloomberg Tech, and Continuum Analytics.
Sorry, I may have missed that.
Oh yeah, so this project, so let me very quickly go. So in our blog, so this was a blog post, our blog post when we unveiled Jupyter Lab, but Bloomberg themselves posted on the Bloomberg blog about the same project, because this has been done in close collaboration with Bloomberg. Bloomberg, by the way, is not a charity. Right?
No.
Bloomberg, in case that wasn't clear, right? Bloomberg is not a charity. Bloomberg is not.
It's almost the definition of the opposite of a charity.
And they're doing this because, and it's been a fantastic collaboration. They're very supportive of open source, right? They have a really, really in-depth in-house expertise. They're deeply committed to the project. All of the work that they do with us is done openly. They support the community. They participate in open forums. But obviously, they're taking these tools and they want to do something with it, and we're totally okay with that. Our tools are BSD, by the way, they're BSD licensed. Everything we do is BSD licensed. So, and what we found is it gives us a lot of penetration and impact in the open community with that approach. But we have very, very productive partnerships with industry, and then they can take this and they can do whatever they want.
But they also contribute back to the tool.
Deeply.
Right.
All these companies that I mentioned are contributing deeply and significantly. There is a problem with the bigger picture of engagement and support between open source and open work and industry. I'm not saying that problem is solved, right? I know
No,
it's
obviously, like, there's politics involved, and there's ethical considerations, and you know, I think in the bio it mentioned that you were part of FSF, so that's why
I'm not part of FSF.
Or you
no, I got an award from FSF. I'm not part.
Okay.
I'm not part of FSF,
Thanks
and I got chided by FSF when I was receiving my award because our stuff is BSD and not BPDM. Right? But we have found that with this licensing approach, we have a lot of impact in open research and education, as I've hopefully shown, and we also manage to engage industry in a productive dialogue.
Which also then contributes to this open science.
Yes.
And you know that. Yeah.
Now this tool, Jupyter Lab, which I think we hope is going to have a big impact in open education and research, would not have been possible without our collaboration, or it might have been taking much longer, who knows. The point is, it has been a very productive and valuable relationship.
Thanks.
So I don't know exactly how the different types of licensing work, but one can, set people or a company or whatever take Jupyter and build a tool on top of it and sell that tool commercially. And if so, given that I think your reasoning to make this is to create impact in the community, have people use it, and really share something great, how does it make you feel if that were to happen? To like make money off of something that you created for as a service, as a great thing for the community?
I don't have a problem with it. I don't have a problem with it because the business of selling software is a lot harder than people think, right? I mean, remember, if you want to take what we have and sell it, you can. But the problem is you're selling something which is already free. And selling is a lot of work. You have to charge people, you have to have customer service, you have to have calls, blah, blah, blah. Building a business is a lot of work. And it's work that right now I am not interested in doing, that I don't have the bandwidth to do. So in order for the business effort on top of these open tools to be viable, you actually have to do something useful on top. You have to do something genuinely useful on top that justifies people buying from you, rather than grabbing it off of GitHub and deploying it on their own, putting it up on Amazon with one click, which is what it takes these days, right? And so I don't have a problem if you decide to do that, because there's a very good chance that in the process of doing that, you're going to find that rather than maintaining a complete fork of everything we're doing so that you can add your little doodads, half of that, you're probably better off sending it back to us and working with us, because then you don't have to maintain it, and it's the foundation gets stronger, and then you isolate the part that you want to develop for your own business. And when I say that, I'm not being hypothetical here. That's exactly what these people are doing, right? That is exactly what they're doing. They are building things on top for their clients and for their customers, but they've decided all of this part of the work, we're better off doing it with these guys in the open, because that way it is part of the foundation that everyone shares, and then they've identified the part that they will actually build a business on. And I don't have a problem with that.
And I'd like to add to that, so I work at IBM, so a lot of the stuff we do
Oh, cool, thank you.
is on top of open source, right?
Mhm.
And a lot of times when we build new tools on top of existing tools, we hire people for the sole purpose of contributing to open source, and then as businesses come in and say, we love this problem, we love Jupyter, but we've got this problem, there's currently nothing there. We assess whether or not it's something that we want to keep as special sauce, that other clients would like to, utilize, that we can sell as a service on top of this, or if it's something better off contributing to open source. And I mean, at the end of the day, software engineers and developers and data scientists need to make money in order to live, so there really isn't anything wrong with it.
No.
The question is, at what point do you contribute something back versus at what point you keep it so that the business can live a job?
No, and I want these efforts to be commercially successful because they will benefit us, but I want to in favor. So this is an example of the project to develop interactive dashboards, which is on the Jupyter Incubator organization, right? It's basically the ability to take a notebook and deploy it without code, only as an interactive data-driven dashboard. This was made by your team. I mean, I don't know what team you work in. I haven't mentioned it, but this is in the official incubator platform developed by the team at IBM. And it's 100% open. I don't know what else IBM is doing with it internally, but that's totally fine. They've done all of this part openly with us.
And then sometimes, we sell it for a while and then we just contribute back to the
Yeah.
source, so it ends up getting generated.
Yeah, which is fine.
Right. One more question.
What's the biggest mistake you've ever made, and why? They just heard me ask the panel yesterday.
Yeah, I make so many. I'm so good at screwing up.
Looking at the internet.
No, that was easy. That was simple. My boss would work out over it again. I would say it's understanding how to scale effectively as the project has grown, and we're still kind of struggling with that, and I am struggling with that. As the project is growing and is transitioning from a small scale effort with a handful of people that talk a lot frequently and that knew everything, to a well-structured community project where now you have to start slicing responsibility, you have to really build areas of work, you have to build teams. So we've hired, with some of the funding that we have, we've hired a new project manager. She started working on the project a few months ago. We're trying to get better at that, but structuring kind of the scaling of that so that you can balance the open commitment to the community where everyone still feels invested and everyone has kind of still a common vision of the project, but you start parceling out things a little bit more effectively so that we don't have kind of the pile-up that is common. Open source communities can be very pile-on, and because everything is out there in the open, everybody can have an opinion on everything. And the peanut gallery can get pretty loud, and it can get somewhat paralyzing. And I think I'm still very much struggling with maintaining that. In my head, I think I have a little bit of a vision of where I what I think of the project, and what I would like it to be, but as I said earlier, I'm not the one doing the work, it's the community. And conveying that in a way that engages everyone, but that creates
Right.
effective
But you have
day-to-day
the
operations.
vision and you're selling the vision.
But I'm not the only one, and by the way, I have a vision.
Right.
But others have a right to also have a vision
That's
in the
fine.
project, right, and to drive it, and they've contributed immense amounts. And so, as I said, I will reiterate, this is not me.
No, I get it.
And,
I'm not saying as you as like the Maleficent leader or anything, but like in the sense that to some extent, well, anyway, we can take it offline.
But that is, I think, that is what I struggle the most with, I would say. And I think I'm very, very intentionally trying to do better, and by having a really good project manager who's doing the project and who's helping us with that, I think we're making progress, but it is a challenge, because it's very much a change of mindset for these communities.
Thanks.
So, I've kept you for way too long. Thank you so much, but I'm gonna be here all day, so if anybody wants to chat or a break or lunch, whatever, I'm happy to. So again, thank you so much.
Thank you.
And my slides are already, I already gave them to the folks, so they're gonna be available in whatever sharing.
Yeah, they are online, so if you go to the agenda, you can,
It's gonna be in the next 2 minutes.
Can you email us the link to the online website?
data mining.
Like workshops without.
Yeah, got it.
But, okay, there's 15 minutes, so